Okay, something that's important that just drives this whole PGF thing is the climate data that we receive from NIWA through the virtual climate network of stations. Indeed, the technology we've developed is highly configured to the information we get from NIWA. So I'd like to introduce Andrew Tait, who's a senior climate scientist with NIWA. I've talked to Andrew over the years about the how the data is developed and what it means. Any inquiry in NIWA eventually gets to Andrew, and Andrew is very, very good at getting back to you and explaining to you exactly what you require. So a thanks for that, Andrew, over the years. And I'd like to pass over to you for your presentation.
I've been asked to talk about the Virtual Climate Station Network. VCSN is also shortened to. There's a number of people that I want to acknowledge from NIWA that have been participants and colleagues of mine over the years. As I was listening to Grant's talk and thinking about the history of this work, it goes back pretty much 20 years. So we had a challenge all those years ago for doing some water quality modelling for ungauged streams. So we had no understanding of what the rainfall was in those small catchments. And so we had to try to come up with a way of estimating what the rainfall was in these small catchments so that we could feed that data into the river flow or the stream flow models, and also therefore feed into the water quality models. We went through a number of different options of looking at how we might do that estimation of rainfall, and the most practical way, and the way that seemed to work as well as any other, or even better than some, was to base their estimates on the actual observations and interpolate or fill in the gaps between those observation sites. So that spatial interpolation process became the basis for the Virtual Climate Station Network, and that was 20 years ago or so. And I started working with Dairy NZ. That's got to be about 15 years ago. And it was with folks like Pierre Burks and Alvaro Romero and Gil and Hemda Levy. Cameron Clark at the time was involved. We started thinking about, how can we use this new data set that we were generating, spatially interpolated climate data at a daily scale, for other applications than what it had originally been envisaged for. And that started a really fruitful collaboration, which is still going today, and it's been fantastic. We've got some papers out of it, and some really useful applications of the data that I would have never thought possible when we first got going on this. So what is the Virtual Climate Station Network? Here's just a part of New Zealand, obviously Taranaki, but it shows you that the Virtual Station Network is just a series of these grid points covering the whole country, where we have interpolated actual observations from climate stations onto that regular grid. And the regular grid is 0.05 degrees lat long, which is approximately 5 kilometres. And there on the right-hand side, I've shown you the variables that we have interpolated. Now, the really great thing about this data set is that these are daily values, values of rainfall, maximum temperature, etc., that we are taking from the observations and interpolating onto this grid. And so it's as if each one of those grid points is a climate station, with those data being available for that location. Hence the name virtual climate stations. And so there's 11,500 of these grid points covering the whole country, and we use a relatively sophisticated interpolation methodology, which was which was tested and applied over in Australia, produced by the software was produced by the Australian National University, ANU, and it's a spline-based interpolation. So it's basically filling in the gaps between observations, but sophisticated in that it takes into account things like topography, for example. So it tries to do a better job than just using the data alone, just in terms of a sort of a bilinear interpolation. As with models, there are some parts of the country where the errors are higher than others, and if you can imagine a smooth interpolation scheme, then where you're in the lowland areas where there's not complex topography, and where you've got you're relatively close to observation sites, that's where you get your highest degree of accuracy. Where you get into the mountains, more complex topography, and where the observation sites are further away, that's where you have your lower accuracy. And so, it's got its warts and all, this data set, but generally speaking, it's got some real benefit as well. We tested it, worked it out to see if it was going to give us the information at a high enough level of accuracy for our particular application that we were concerned with to start with, and felt that it was a goer. And so we set up a system where every single day these daily values are interpolated onto this grid, and that's done now automatically. And that means, these data are now part of a database, the National Climate Database, as a derived product. We went all the way back to 1960 for rainfall. We didn't go that far back for most of the other variables on that list on the right. We went back to 1972, and that was because actually still, although we're working on it and have been working on it for many, many years, there's still a lot of daily values pre-1972 when the database was set up that are still on paper records and not as digital data. So it's getting better and better as we backfill that catalogue of paper records. But it was easiest to start the VCSN data sets in 1972 when we had the actual digital records in the database for many, many sites around the country. Wind was a little bit special as well because it was there were different measuring, different instruments and different ways of measuring wind and different heights, etc. And they only kind of got standardized around 1997. So we start the VCSN for wind speed in 1997. It really has been now, over those 20 years, the basis for many products. So not just in the modeling sense in terms of water quality and water quantity, but because it's spatially consistent and temporally consistent climate data, it's now been used for, within NIWA, things like the 15-day forecasts, which became part of the Pasture Growth Forecaster as well, seasonal outlooks, and even climate change projections. And there's the URL down the bottom there. Just if you Google virtual climate station network, you'll find that it gives a little bit more background on the VCSN data. So what do you get? What do these data look like? Well, this is a Excel spreadsheet that I can extract from CliFlow. It's not publicly accessible. It used to be, but it's not anymore. But I can talk to you about that in a minute. But this is the type of output or what you would get from a particular location. I just chose a site here. So you have site information, then you have some notes on the actual variables and the units, and then the data. And now the key with the data is that there are no gaps, which has been really important for many of the applications that the data set has been used for, that you don't have to try to fill in missing observations. Because essentially what it's doing is it's saying, well, how many, look at across the whole country on a particular day, take whatever data is observed and do the interpolation. Now that has its benefits and its costs in that over time you'll have some climate stations closing down, others opening up, and certainly there will be times at a climate station where the data, the instrument fails, or for some other reason you'll have a data gap. The interpolation will still happen, but that will have an impact on the accuracy of the VCSN data at different locations. We haven't tried to correct for that. We basically say, this is the best information that we can derive on any day. It does have some, like I said, warts that are impacted by stations opening and closing over time, and that just needs to be taken into consideration when you're using the data. And in fact, we've had some really good collaboration with Dairy NZ where we've looked at trends and things like that over time, and done some work to try to improve our estimates, our climate estimates, using some local scale observations that haven't been used in the interpolation, and that's worked really well. How good is it? Well, that's a good question, and it really does depend on where you are. So we've done written a few papers on the process of doing the interpolations for different variables and doing some validation work. Like I said, rainfall in particular is probably the trickiest variable to interpolate because it can be quite variable over time and space. And here's an example of a high elevation site that was on in the Southern Alps, and just gives you a sort of an impression, I suppose, that with the dark coloured bars are the actual observations and the light coloured bars are the VCSN estimated observation at the closest VCSN grid point. We're certainly getting the timing of events generally right, which is to be expected. When there's no rainfall, you're interpolating zeros everywhere. But in some cases, we're certainly underestimating, and in some cases, we're even overestimating the rainfall. But generally speaking, it's giving a reasonable representation of rain, even at high elevations. When you go down to lower elevation sites, so here's one right down on the coast on the South Island, your reliability, your accuracy of the interpolation improves markedly, and you really are not only getting the timing of events capturing quite well, but you're also getting the magnitude of events pretty good as well. And here's another example of a coastal site on the west coast of the South Island, even with complex terrain close by, and so you're getting much more orographic effects of rainfall. Here you're still getting a reasonable representation of the timing and magnitude of rain. We did a bit of a study on what that kind of means when you sort of average it out across the country, and generally speaking, for areas below about 500 meters elevation, the mean absolute error of daily rain is in that sort of 2 to 4 millimeters for VCSN data greater than or equal to 1 millimeter. So, but if you look only at more the sort of heavier rain days, when you're getting greater than 40 millimeters of rain, then your error is around 8 to 12 millimeters. So in terms of relatively speaking, it's similar, but you certainly get a greater error when you get more rain. We've looked at other variables as well. Here's another one just to show you where we looked at potential evapotranspiration, and the map on the right-hand side is the locations of 20 sites that we took out of the interpolation. So we did the PET interpolation without all of the data from these key long-term sites. So we were actually degrading the product by doing that. But then we could validate the interpolated PET at those sites as it was an independent data set. And you can see averaged over those 20 sites, the darker grey bars are the average root mean square error this time. And that's in the order of less than half a millimetre to a millimetre per day is your approximate uncertainty there, and the lighter grey bars are your average daily PET. So in summer, that's around 4 millimetres, and it comes down to that sort of 1 millimetre to half a millimetre in winter. And the line then, therefore, is the relative error. And so, relatively speaking, in summer, you're kind of in that 25% error range of the daily PET, but in winter, because the magnitude of the PET is closer to the error, then you're getting up into that sort of 70% range. So there is uncertainty with this information, of course, but then you've got to just take that as it is and see if it's going to be valuable for your particular application or not. And that's really what has happened with the collaboration with Dairy NZ, which has been fantastic. So in the old days, you used to be able to get a hold of the VCSN data through our climate data portal, or the National Climate Database portal, CliFlow. You can no longer get it through that portal, but we do have another paid service portal called NIWA Data. We're actually going through a process now of evaluating this whole portal once again and seeing if it can be either improved or incorporated into another mechanism. But at the moment, you can certainly get access to VCSN data through this portal. It's a paid service. If you've got a project where you're looking for a large amount of VCSN data, then talk to me about how we can set up access for it. That's exactly the way that we do it with Rosair now. We have a contract. Rosair has a contract with us to access the data that goes into the forecaster model. Now, just rounding off this presentation with some points on where we're going with this. I mean, it's been 20 years in the making. We've done some various iterations to the interpolation scheme. We've certainly added variables over time. But the latest quite exciting area of research that we're doing here is that not all of the rainfall data that's collected in New Zealand comes into NIWA, into the National Climate Database. Which is sort of a issue for New Zealand, and we're trying to resolve it, but it is what it is. Many of the regional councils across the country collect a lot of rainfall data that they use for their own purposes, particularly hydrological modelling, and that rainfall data is kept in-house in the council and doesn't come into the National Climate Database that NIWA maintain. But we worked with the regional councils to gain access to a lot of that rainfall data, historical chunks, if you like, not real-time access, so that we could do some more evaluation of how the VCSN rainfall set could be enhanced, the errors reduced, just by adding in all of this extra data. And you can see here this plot on the right-hand side that the CLIDB number of rainfall stations in CLIDB has been falling over the last few decades as all of those manual sites really closed down. Almost all of our rainfall data now is automated sites. There are still some manual sites that we do get on a monthly basis, and they get absorbed into the sort of rerun of the VCSN that's done on a monthly basis. But there's also this amazing number or growth of rainfall observations at regional councils over the same period. And if we were to incorporate both data sets, then we have a kind of a consistent level of, over 1,000 sites across the country, which we're now seeing if that, what the benefit of that is to the accuracy of the rainfall interpolation. There's a lot of work that had to go into, first go into the process of agreeing to get access to those data. One of the real benefits is many of those sites are at high elevation locations because they specifically, the locations have been specifically chosen for hydrology. So that nicely also complements the geography of where the climate stations from NIWA and Met Service are located, which is much more low elevation sites. There's been a heck of a lot of work now just to get the data into the format that we need. There was a lot of work to quality control the rainfall data, but that's all happened. So we've had this big chunk of historic data now, and running it now through ANU Spline to see what the benefit is with the additional data. By agreement, the regional council data itself isn't in CliDB, just all of the site metadata, and then we're using the actual observations only for the purpose of evaluating, how much improved the estimates, rainfall estimates, could be by incorporating it. And we're using as our metric to test the increased benefit of those sites. We're using river flow observations and modelled river flow, because if you improve your rainfall interpolation or your rainfall estimates, then you're going to get a downstream, pardon the pun, benefit in your estimate of river flow. So that's an ongoing project. It is taking quite some time. There's a lot of issues around data and politics, but I think it really is. I'm pretty sure it really will demonstrate that in order to get the best possible estimate of rainfall, you really do need all of the available data. And what we would therefore need is to have all of that rainfall data operationally into the database, so we can run the VCSN in an operational automated process as it is at the moment. The other thing that's happening in the next few years is we are looking at basically hindcasting or running our weather model in a historic mode, going back to 1990 and running it. So the picture there you can see is just for a single year, where we've averaged the VCSN rainfall in the left-hand picture, and the right-hand picture shows the similar period, similar year of rainfall from our New Zealand convective scale weather model, NZCSM. And so what we're going to do now is going to run this weather model back in time and generate what's called a reanalysis data set starting in 1990 and going forward. So it's going to be a similar type of product really to the VCSN, in that you've got a spatially complete and temporally complete estimate of rainfall everywhere in New Zealand, but now it's based on a weather model rather than observations. Now, of course, the weather model itself is validated based on observations. So the actual observational data set is sort of incorporated into, if you like, the weather model data as a way of fine-tuning and calibrating, validating that model. So it kind of gives you the best of both worlds, really. And the other thing that it gives you is that the resolution is now, we're running this weather model at 1.5 kilometre spatial resolution. So going from 5 kilometres of VCSN to 1.5 kilometres is a significant increase in the resolution. And it's also, there's an increase in the temporal resolution. So instead of daily values, we've got 6 hourly values. So there's a real potential there to, understand sub-daily rainfall patterns and what that might mean for example, for pasture. Of less probably interest to you is that there's also multiple layers in the atmosphere in these models, so we can we're not limited to just surface-based observations. And another key is that in the model, because it's a dynamic weather model, basically showing the progression of weather systems as they pass over New Zealand, whether the rain-bearing system or an anticyclone or wind coming in from the northeast and then changing to the south, etc. Everything is dynamically interconnected. So the rainfall is falling, when the humidity rises and when the cloud cover increases and when the front comes through, the temperature drops. Everything is perfectly dynamically interconnected. Whereas if you think about the way that we do the virtual climate station network, there's an independence of all of the variables. We interpolate the rainfall independently of interpolating the temperature, independently of interpolating the wind speed, etc. So there's and it does happen from time to time. You do get sometimes these inconsistencies between the variables because of that independence. With the weather model, you don't get any of that. So that's another real benefit. So I think probably over the next couple of years, we will have got the reanalysis data set completed. And that's another opportunity, I think, for us to collaborate and look at what are the benefits of maybe using that reanalysis data set, that dynamically produced weather model data into the forecasting system, the pasture growth forecasting system. So I just want to thank you, and just list some of my colleagues there that have worked hard on the VCSN over time and who are currently sort of taking over from me for doing it. I'm kind of moving on to do other things now, but it has been a really exciting and interesting collaboration working with Dairy NZ over all of these years, and I'm really looking forward to it continuing as much as we can. So with that, thank you very much.
Thank you very much, Andrew. I just see time-wise we won't have time for questions, but the speakers will be coming up and we'll have a panel discussion at the end, so just hold those questions.